Hello.
Hey, how are you?
I'm good. I'm good. Yeah, looks like there wasn't much activity in the Slack, so I'm concerned that people are maybe not that involved.
I guess it's hard to say. I haven't really done these sort of study group before. Do they? I mean, I'm just wondering if
Good question.
people.
Actually, like I think David Collier's expectation is very active participation, and that might just be unique to some groups. And that's a good point. We should maybe talk about that. Some groups are very directed, very specific, and some are a little more loose. It's a good topic to review. It depends on the material and maybe everyone's familiarity with the material, things like that. Flavor.
Yeah, I think because I don't have so far. I've been understanding it fine, so I don't know whether I should expect people to talk more if they
I know.
understand it already, or
Right. It's hard, and we should maybe as a group maybe come to some observations and things like that. I'm just now just like in the last few days, just literally able to take the homework material, create the graph in Colab, and begin to do things with it. I'm nowhere near able to even do the last part of the homework, doing an actual project, although I am understanding the slides, so it's
I
again,
think
it's
like doing the homework does definitely takes a lot more thought than just the slide. So I think maybe when we get more towards the later homeworks, there'll be more discussion because stuff is just harder. Like because if you look at homework 0, it's just more or less reading up on the Network X or Snap APIs, and that is kind of a bit less.
I beg to differ a little bit. I'm like
Really?
I'm just like trying to understand what exactly do they mean by directed edge, because in the example it looks like this, but you go to use Network X and you're kind of like, is that a directed edge because it doesn't go both ways, or that kind of, I'm deliberating as I'm doing the homework, which is good. I mean, that's important. I kind of, that's just me. My personality is I have to know everything and have no questions or I can't proceed.
Uh-huh.
So
Well, I think kind of that's sort of the thing that we'll probably want to actually discuss in Slack.
I know I should have participated earlier in the week to the degree that I finally did literally last night and this morning, because now I'm at a point where I have about 10 questions that are probably pretty easy, and like this, David, is it Collier? Let me see, DC San, I think it's David. He had just a little discussion about, throughout some question about reciprocal nodes and things like that. That's good. I like that kind of chat in Slack that actually has questions and answers that are simple if they need to be for people like me that are, the graph is new. So
yeah, and even like what David pointed out, I mean, kind of, it's sort of like it's very useful for me because I never thought of it that way. But actually, yeah, it does make sense once you point it out. It's a bit like code review, where someone pointed out that you're,
Right.
hey, have you thought of it this way, sort of thing.
Right. And I just literally did that exercise, the reciprocal nodes, and I have a question, and it doesn't seem reasonable. The answer I get out of that particular graph doesn't seem reasonable. So I guess that's why we're why we meet and that kind of thing. So
So, sorry, I joined late. So, are we talking about the first like homework 0
yes,
from the 2019 one? I couldn't get on to it. Like, I could finish 1 and 0 and 1 collab, but yes, I have to do that.
yes, I think we got HW0, which is that PDF that starts out pretty simple, then gets harder, and then collab 1 also kind of has that same kind of is fairly simple to run through, but you still have to spend time doing the work, right?
Yeah, collab 1 almost I could finish. I think the last question, I think question 6.
Oh yeah, collab 1 was actually hard. I mean, you had to blow through an actual, I guess, a neural network of I've never heard of embedded layers before. So that was all new to me. I've seen them, but never used them. And so we can go.
Yeah. I had one question, like if you could, you were able to understand what does question 6 want, because I was not able to understand. If I don't have a reference point in a graph, how can I define the negative edges
Yes.
in general? So I don't know whether like you might find it stupid, but I couldn't understand like what they are trying to say, what it's trying to say in question 6.
I agree. I agree. The whole, I guess the concept of the negative edges is a little bit bizarre, but it makes so much sense when you think about why it was constructed, trying to go through and figure out the probabilities of events happening through the walk, which is really very interesting. But then using it in collab 1 got a little, like I just did what they said and it seemed to work. Although I think I got different answers than the one guy that actually put his collabs on GitHub. I think we have kind of access to that one fellow. If I can find my link. Yeah, if you remember, we did find a GitHub repo of all of the collabs.
Okay.
Yeah, and I don't want to give it away unless, Wendy, what do you think about that? Is that pretty much just open?
I mean, I don't have any specific opinion. I mean, I won't necessarily just trust someone's random solution on GitHub.
True. Yeah, obviously. I'll also check from my side, but
yeah, good point.
I think it's
so
great.
Maybe like it's my understanding is a bit wrong in the negative edges part. So if I have a graph, just like hear me out. So if I have a graph G, which is let's assume it's a karate network, and can I have negative samples without specifying the node in which I am standing? Maybe like without having a reference node, how can I define the negative edges without having a reference node myself? So I couldn't understand that part.
I thought, I mean, I might be completely wrong, but I thought that they defined the negative nodes as just a random sampling of all the other nodes in the graph, because the idea being that if your graph is big enough, then you're less likely to come across them in your random walk. So I just assumed that negative edge is just pick a random bunch of edges from the graph.
So then it is not exactly different from sampling. So if I want maybe 6 negative edges, that it's not different from sampling random 6 edges in the whole graph. So
I think that's true. I think the concept of a negative edge is every possible edge that isn't an existing edge, right?
Yeah, like so if I'm what I understand, like I remember the negative sampling from from NLP, where I have a word and I take a window of maybe size W on both sides. What I want that I want a distribution of the words in the negative sampling, which, if I understand it correctly, correct me if I'm wrong, which are not in that window. So I'm using that as some sort of like that the window. I mean, I am at that specific word, that is my reference word. I have that window. And when I'm trying to like predict the other words based on the center word, I think it was skip gram model. So
Mhm.
my in that my negative sample is the words which are outside that window, which are basically not here.
Right.
So is my understanding correct if I talk about this negative sampling there?
Yes, I think so, because every negative sample has two nodes. And so you're just specifying the negative samples of which from the node you're on.
Yeah,
Yeah,
exactly.
yeah, yes. So that's
So
valid.
so when I go for question 6, it wants me to define. Let me just share my screen, maybe. Where am I? Yeah, sure. Yeah. So if I look at this, is my monitor visible?
Yep.
Yeah. So you see the definition of the sample negative edges is between G and number of negative samples what we want. Now, my point, the issue what baffled me is that where am I putting the reference node in this sampling? So if I want to sample some negative edges, I have to figure out like where am I standing? It could be a
Right.
big network. So as Wendy was saying that maybe it is trying to sample some random distribution. Now then my question is how it is different from a random distribution? Why we are calling it sample negative edges if it's just sample of edges?
Well, they're not
And then
all edges. Yeah.
then it asks also this question, which of these edges can be negative ones? Now, if I don't have a reference point where I'm standing, how do I know that some edge is negative edge or not? Like, how do I see the contrast between the, if I say positive edge, maybe which are connected or which are maybe uh, X steps away from where I am standing, and those which are basically away, which are maybe on other side of the world? How do I know? Like, how do I see the contrast there, and how do I answer this question? So this is totally like I'm bored by this question.
Right. I mean, so which of the following? So those are negative edges because they appear in the negative edge list, right?
I mean,
Oh, yeah. So did you do the next part?
Yeah. Then I
Oh,
moved to
okay. No.
basically find out.
Okay, but wait. You have to. Did you? The negative edge list is a function that I think
This.
you could come up with. That was an earlier question. Maybe, right? Negative edge list. Negative edge list.
I guess this is the.
Oh.
Yeah.
Oh,
No.
no.
This is the first.
Well, okay. So the positive edges. That's something we know about, right? Yes. So if it's not in the positive edge list, it must be a negative edge.
But how are you defining positive edge here? Like
that's given to us, right?
Oh, I wonder if it's like is it that you just sample from the permutation of all the possible links between the nodes, and then you remove the ones that are real?
So yeah, okay. So are we saying the positive edges are those edges which exist in the graph, and negative edges are those who like we can like basically define based on permutation, as Wendy was saying, but they do not exist.
Precisely. It's the ones that don't
exist.
Okay.
Okay.
And it's all the ones that don't exist. So the negative edge list that he gave us, you just tested against the positive edge list.
Okay. Just let me note it down. So yeah, I basically like I was thinking a lot on this and tried to figure out, but I think that my understanding was not correct.
Right.
So okay, so basically he's using that to see. So so after what is the whole idea? What is the vision behind positive and negative edge sampling? What are we trying to find the contrast here between the graph which exists and graph which which is basically if I say all the combination, I mean if I say take a graph with all possibilities, all possible edges, it's like negative. I mean I'm subtracting that. If I say at u minus positive edges, that is a negative edge. So what are we trying to figure out here? What does it give us if I sample that?
Well, as
Well,
I
it's
understand,
more for the node embedding node to fact things where
yes.
like you sample from. So if you compute everything, like the loss over all the graph, the whole graph is really expensive. But basically, like you just need to sample like five. I think they say between 5 to 20 of the negative ones, and then that's enough to give you a loss function that converges to a decent value.
Yes. So imagine you were trying to estimate the distribution of something. And of course you care about the positive edges, especially the ones that are nearby. Okay, but then you also care about the distribution over the negative edges. But there's no way you could possibly do all of them. So you just care about a sampling, and they do say 5 to 20. And that gives your loss function enough to accurately continue to converge.
Okay. Yes.
I'm not sure I understand the actual part about what you do to a negative edge, but I do understand, like during a walk, you care about both the possibility of coming across doing things to edges that do exist, and I guess doing things to edges that don't exist. But that's, to me, still a very fuzzy concept.
So I think like if I say that I have maybe n number of points nodes, and the possible edges between them is basically combination of all possible pairs which exist.
Very
Now
dense.
if I so if I maybe initiate an embedding of a maybe d dimension which is less than n or maybe greater than n, let's not care about what is the dimension of the embedding. And let's if I like initiate it with a uniform weights and all the possible on the all possible points in that embedding, then I am assuming that we can take it analogous to that we are giving all possible combinations between different nodes as equal value that they exist. Now so based on the positive and negative edges, based on the contrast between them, we can train that embedding so that in the end the distribution of the values, the distribution of the weights in that embedding adjusts itself that way that it can represent, that embedding can represent that graph. That is what I think is trying to do.
Okay, that makes sense. The embeddings represent some distribution from node to node, sort of.
Right. Yeah. So if all embeddings are same, then it means like all possible there is no specific structure to the graph. It is like all edges exist.
That's right. Going in one dimension is the number of nodes. Yeah.
Yeah. So if I start like training it against positive and negative edges, then I am giving more weightage to those latent like variables in that embedding which represent those positive nodes, and I am reducing the weights of the those parts in the embedding which are which are basically which relate to the negative edges.
Right. Through
and
the
based
dot,
on this
the dot product. Does the dot product surface that relationship in that sense?
could be. So I'm not thinking about the like way in which we are going. I'm still like, it's a very abstract thought I'm having. It's like, so what we're trying to what I think we are trying to understand here is have some sort of a contrastic learning where we are trying to lower the energy of the in that hyperspace, lower the energy of that on that embedding, on that manifold where that graph exists. I mean the structure of graph representation versus those that does not exist. So those edges do not exist, they have a higher energy, and those which have a lower energy are basically connected to the positive edges.
Right. I think you've hit upon it perfectly, because that's precisely what the algorithm does. It iterates through, but it does adjust the weights of those embeddings. The negative space, I guess it doesn't. How does it? Well, they don't exist. So that's the part that's a little bit mysterious to me. But I do understand what you're saying about the it raises the energy of the positive space, at the same time reduces the energy of the negative space, giving you the ability to predict.
See, okay, if you look here, so we are taking loss function is binary cross entropy, and now we are trying to predict what edges exist. So he is using the binary cross entropy between, okay, loss function. What is the loss function? Train.
You have to actually, it's actually another part of the lesson.
Yeah. I guess yeah. So when you so in fact that thought didn't have, like, was not exactly in my mind when you mentioned that what exactly negative edges are. Then I could relate it with the binary cross entropy. Now I understand why he's using binary cross entropy. Like, that wasn't really clear to me initially.
And a sigmoid function for the activation.
Cool. Okay. I guess that's what is happening here.
Yep. And I did the lesson just like it is, and I put in the things, and it started to train. But exactly. I got different answers than what the other guy did, and the visualization of the separation wasn't quite. It didn't seem to group very well.
I think I have not completed this part. This one I have to finish this one. I haven't coded it in.
Right.
But we can look at this one. It was there in the whole one whole this iteration was there in the training cycle, was there in the part 1. So yeah, so train optimizes zero grad out model data. This is lossy. He's taking the criteria of train mask and y train mask, and what are x and y basically. Those are basically positive and negative edges, are they? No, it's a bit different thing. It's a bit different. Here we are trying to classify. I think here we have to finish the code. Maybe we can have a peek here. And what he has done.
There you go. You could cheat there and look. That's what
no,
I did.
the last one. I just want to. Okay, just the last one.
Like my loss function was trained very quickly. Like the accuracy was 1.0 on the first epoch, on the very first epoch, which I know is not true.
1.0. Okay. That's surprising.
It is. So I think my algorithm is a little broken, but it still worked, and I was always amazed sometimes when you can just pass a what is it, a torch, not a vector, a thing into a function.
Okay, maybe I'll look it later, like after doing my by myself. So hopefully that will help me understand.
A tensor. The tensors are just, I get scared by them, and then all of a sudden they just work like objects. You just pass them in and they do their thing. Okay.
With tensors I always have issue with the dimension thing, because they add another level of complexity. Most of the time when I'm looking at the differentiation or the calculus, I'm basically looking at the tensor, not the mathematics at all. I mean the dimensions of the tensor. If they match, I'm happy.
Right.
That's it.
Yep. So okay, I just coded collab 1 just like it kind of said, and it started to work, but I don't like. I haven't really compared my answers to the other one, so I don't really have a good feel for that. So
what does it mean by predicted value greater than 0.5 will be classified as label 1, else it will be classified as label 0? What does this label represent? I think I'm missing something there.
Label is like just 0 is the negative edges.
Okay, so they do not exist. That's it, right?
Yes.
Okay, that's it. Right? Okay, cool.
I think
we have. Okay. I think we have understood this one then.
Yeah.
And what else was on this CS224W? This was okay. Even I had figured search for solutions. I should not be. So GN. Yeah, page rank. This one was.
Oh, that
I think
was,
this.
it's a whole nother. Oh gosh, no, I'm not even close to even homework. Well, homework, hold on now. Homework 1 from the previous lesson is not that one.
No, I'm not looking at this one. I was
Okay.
looking like what was in this week's thing.
It's 5. They are you? Yeah, it's a lecture 5, like label propagation for node classification. So it's like the iterative classifier, relational classifier, loopy belief propagation thing.
I haven't even started on that. I got through page rank a long time ago, but yeah. So we could review that if you like.
Yeah, we can review the page.
I do think this little lesson in running a model is very good. I'm going to try to figure out why mine is different than the one that's been posted.
Yeah, I also share this one. Like now that you are like, I have understood a bit of negative and positive ones. So I'll try to run this and maybe
good.
post it.
Okay, good. Now homework 0. I don't know if anybody wants to review that. But
oh, sorry, yeah, I haven't done that. But yeah, if you have like, you can share it.
They say it's pretty easy. Although I just had questions about his, the way it was presented in that overhead. Okay, I'll just go ahead and share, and then after about 10 minutes, we'll go into the lesson 5.
Sure.
Because I didn't look at it, so I'm not going to be able to help. But let me see, how do you share your screen in this tool? Sharing screen. Hello, share screen. Okay, then I got to choose a screen. Oh Lord, let's see that. Share. Okay. Get out of the way. So the question here was, he gives you an example of, okay, here's the little e small where he has examples of number of nodes. Got that. There's 1, 2, and 3. Understood. Number of directed edges. Okay, so directed edges are any edge that's not a self loop, right? So that's these 3. Great. Now, in our code, in the wrong lesson. So this guy did it. I guess everyone was able to read in. You have to download, of course, this wiki data set. And then I read it into a node and into a graph, and then made that graph be a digraph by reading it into a different one. There may be a more direct way to do this, but this I think worked for me, because then I could effectively construct a new graph that was a directed graph from the nodes that were in this graph.
The other option is that you can put it directly into the read access option. Like if you pass in create using as a
can you use the file directly?
Yeah, so basically if you look at the documentation for read edge list, there's a keyword argument called create underscore using, and then you just pass in the
file.
If you type nx.read underscore edge list and then double question mark and then look at the documentation.
Oh, okay.
If
you said there was a using. Right.
No, if you go back to cell 7.
Go back to cell 7. Got it.
Okay. If you hover over it, like hover over read edge list, I think if you look at the documentation, then you can see create underscore using the key, and that's basically if you pass in the function example and then you nx.dir graph instead of nx.graph, then you can just get a direction graph from it. But I mean, your way works as well. But if you want to do it, gap,
Got it.
then
I see. This could also have been a set of node pairs. It just happens to know how to deal with. Okay, got it. Okay. Well, anyway, so of course the number of nodes. There's obviously 7115 of these nodes. Made sure it was a directed graph. No self loops. So that means nobody voted for themselves to be on the board. I guess that makes sense. The number of directed edges. So that's where I guess that's where I kind of started to not understand what exactly was the difference between an undirected and a directed with respect to how it was described. So undirected is just the number of votes, right? That anyone gave to anyone.
Right. It's like pairwise, how many edges exist.
Okay,
Right.
That's this one. That's a big number. 100,000 votes were cast by some people. It doesn't even mean that everyone voted, because I guess that's what out degree and in degree is gonna. So, okay, I don't know what a directed. What are the directed edges? If this is the number of votes cast, the number of undirected edges, what's the number of directed edges? I'm just trying to simply do exactly what the homework kind of laid out. Directed edges, the number of ordered pairs for which A is not B. Isn't that the undirected as well?
I think the thing is,
So like
no,
a directed A-B pair is different from a directed BA pair, but for undirected edges it will be same. So that's what the point 4 says. The number of undirected edges in network, the number of unique unordered pairs. So ordering doesn't matter, but in directed one, ordering matters. But yeah.
Okay. Oh, okay. So what is the answer? How does one get to? This is wrong. I don't think this is right, because I just chose the out degree. I just thought, well, everybody voted, so that's wrong.
That's a function called number of edges.
Yeah.
Well, that's just edges, right?
So if it's a directed graph, that will be number of what do you say, directed edges. So if you can say that like an undirected edge is equivalent to 2 directed edges.
I don't know about that. Okay, so this can't be true. I doubt that the number of directed edges is the same as the number of undirected edges. But that's exactly what I'm saying. I don't think I understand how, for example, how can we have an undirected edge in a directed graph?
So if you like print GD dot edges for undirected as well as directed graphs, so you can see that they have some ordering. So whenever you
they look like this. Yep, understood.
So I think because like in a directed graph, like for example, I've got 3 nodes, then say the edges are 1, 3, and 1, 2. 1, 2, 3, and 1, 2, 2. Then it's kind of, it doesn't mean that 3, 1 is an edge. So 3, 1 is not an edge in the directed graph.
That's right. But is it so that's why I was kind of wondering, how can they ask how many undirected edges are in a directed graph? They don't exist. It's all directed.
Yeah, there will be ordering.
No, but it means that like if you ignore the ordering, how many edges are there?
Yeah. So the number of edges in both cases are same, but just that we are assuming that the ordering doesn't matter in undirected ones. So maybe that's how the graph is prepared. So you can print the GD for a directed graph also, the list of edges, and for undirected graph also list of edges. I mean, if the source is same, they're coming from the same source. But in the directed edges, it will make sure that the ordering does not. I mean, ordering matters, but in undirected one, it will make sure that the pairwise combination is not repeated. But
Okay.
because here it is already defined, the edges are defined. The way it is, what I feel, what I think, and what I like based on the karate network, I understood that the way it is defining the ordering of the direction of the edges is based on the way it is the graph has the
Yes.
like edges defined. So if
Yeah.
it had defined 1 3 as 3 1, it wouldn't matter for the directed or directed one, but it matters for the directed ones.
Okay.
So
And
that's why
that,
it is giving you the those
with,
values, same value.
with respect to the intent of the network, which is in this case a voting network, where one node casts a vote to the other node explicitly. That's the relationship. Okay. Well, that was confusing, but okay. Thank you for that. And then I guess this is the reciprocated edges, and I'm figuring you just go through all the edges, get the pair, and then you look back and see if the other pair exists.
True. I
Right?
think that will.
Yeah.
Well, there's none, literally zero.
Yeah. So if you I think the reason behind that would be because when you read the graph, it is I believe it's a not a directed graph initially when you read, but that should not
Oh,
happen.
no. That's a
I
very good point, though.
I got around 5,854 reciprocal edges.
I wonder. No, that's a good point, because this says that if number 3 voted for 28, it's possible that 28 voted for 3. Very possible, but it may not be true. I don't know, but I think you might be onto something. The fact that I read it in from an undirected version, maybe that did.
That would affect it, because it
Oh,
will remove all the repetition of the edges, what I believe. You can try like
thank
reading
you.
the other ways. I haven't done that, but that is my inkling, what I think.
So I could do a using here somehow.
No,
So yeah,
the number in cell 7, not this one.
I'm sorry. Yeah. I don't know what to use. Using,
Create underscore using.
create.
I think you need the path first. I think like create using has to come after the path.
You might be right. The way it is, it might have to. Well, yeah. It's just we'll create. Oh, now it's
And nx dot diagraph.
yeah. So maybe when you read it as a undirected graph, it already lost that information of the direction of the edges. Then when it is converted into a directed one, it you don't get that information back.
Okay. All this is my GD now. I definitely okay. So if that's true, then I should be able to go right to this code.
Okay. Yeah.
And have it come out with a new answer. No way. Good
Cool.
job. Thank you so much. Wow. Well, that was tricky. That little thing. Boy, I thought I was doing everything right. Okay. Well, we learned something, didn't we?
Yeah, discussion always helps.
What did this thing spit out? What did this spit out right here?
So it will
oh, it went both ways. It went both ways. No.
No, as you said, there was no reciprocating edge. I think it was you were getting 0, is it?
Yes.
Earlier.
Oh, it filtered them out. It literally filtered them out.
Them out. Yeah. So it filtered whenever there was 1 3 and 3 1. It only kept one of that pair.
Yes. It says, I know you. I know this relationship. Okay.
Yeah. So like.
Great. Okay. Well, that explains. I was really starting to wonder what I was doing wrong. And that will also help everything else, I'll bet. Well, maybe not. Okay. Well, that's about as far as I got. And then I just started to work through the out degree, and that was fairly easy. But my stuff is all broken now. Let me see if that changes. Oh, it did. It reduced it. That makes sense. Anybody agreeing with out degree numbers and in degree numbers? So only 1,000 of the nodes voted.
Yeah, that's what.
No, only 1,000 didn't vote. Out of all the people, 1,000 did not vote.
Yeah, 0 out degree. Correct.
And out of all 7,000 participants, this many did not receive any votes to be on the board.
Anyway,
Okay,
okay.
that's as far as I got. So, okay, what we can switch to the lesson 5 if you want.
Sure.
I'm sure the meat of this work is down here in the stuff I didn't do. Right. So this, I might still continue with this. Sujit said he did it and found it easy. Like, oh, come on.
Well, he seems very knowledgeable about this
I
stuff
know.
already, so that's probably why.
Yeah.
Okay. So
I
I
saw on
don't,
LinkedIn there's a book he has written already on that. No,
Yeah.
not on exactly on this, but I guess he's pretty much have been working on these.
right. That's great. Okay. So I'll stop sharing. If Wendy, you want to maybe entertain us for the most current material.
Do you want to share the slides? Because I think you've already got them.
Oh, yeah. Do I have them up? I'm not sure.
Yeah,
do.
I have.
Okay.
This is share.
I think because I'm doing the meeting on an iPad and the stuff is on my computer, so I need to like rejoin again, which is like annoying. But my computer doesn't have a webcam, and I just like can't be bothered to install a webcam.
Cool. So I think this was the one. I had to open this tab and one more tab. So this is the correct one, like right? Link page rank. Yeah. This is the one we want to go through, right? 4th page rank.
4 was page rank and 5 is the other one.
The message passing and node classification.
Yeah, message. Yeah. Yeah, I think someone was talking about message passing in last meet. Sujit.
Yeah, that's right.
So
I think
is it like
passing,
hello?
yeah. So I think message passing basically goes through the whole course really, because it's such a core concept of the whole like graph neural nets, graph learning thing.
Mm-hmm.
I mean, so many of the algorithms is just message passing in disguise one way or the other.
Right. Trying to just pass information about one part of the network through somehow to other parts, which is fascinating. So I look forward to knowing this.
So like my screen is visible, is it?
I see it.
Yeah.
Yeah. Okay. Cool. Okay. So yeah, he starts with, I guess these are the embedding fun. Okay.
Good old adjacency matrix.
Agency matrix. Yes, I guess this is the agency matrix. Okay. Sorry. Oh, okay.
Yeah.
So he gives some example about the web. This was the basically getting the context right.
Mm-hmm.
By giving the example of the World Wide Web, where he was taking the nodes as web pages and edges as hyperlinks. So those are the connections between them. Now the basic idea was to define. He goes on these areas also. Dark matter is there, we don't see it, but in general, let's focus on the visible web here.
Mm-hmm.
And yeah, so then he started giving some example about the how you define how can you define the value of some edges. This was about history, and yep.
Mm-hmm.
So this is a directed graph he mentioned, and the web can be also thought as a directed graph. And basically, one website, how it is directing to another website. So
Right.
if there is an important website, it will have incoming channels from multiple important websites. But if it's indirect, not that much indirect, that much important website, it won't have so much input, incoming edges, and not. And if they are coming, they won't be coming from very important web. Now the point is how to define the importance of a node there. Those are the web pages.
Right.
Again,
So
more
reputation or something. Citations, reputation.
Citation.
Yeah.
Then also encyclopedia pages. Again, don't know for it. Yeah, so web is a directed graph again, like because from one page we are directed to another page. That's a
Out-
one-way link.
out-
That
Outlinked.
that
Yeah.
may not be other way around. Correct?
Yep. Yep. Got it.
Yeah. Okay. So map of the web. This was the point. All web pages are not equally important. This person does not exist versus Stanford.edu.
Yeah, I think this person does not exist is way more important than Stanford.
Nowadays,
I
right?
love that. I love those pages. Those are great. Those are just fun. Fun.
Yeah. Recently, like I think 1 hour before, I was reading on Reddit. Someone wants to make this like this portrait does not exist. Like some based on some historical imagery, how it was painted. He wants to make a website, and he does not know any architecture. He has no idea.
Oh, that's
And then, but he
awesome.
wants it. So I was like, okay, that's a nice concept. You have to do some
I like
transfer.
that. Yeah, it's just very similar.
Yeah,
You can do
you can
some.
use the same model, in fact, but,
Yep.
and maybe on just slap like some the style transfer. You can do the style transfer. In fact, use
Yes.
the
Yes.
you can use this person does not exist as a like a
Oh,
page to generate pages
merge it
and
together.
merge it.
Yes. Because I did a thing with style transfer. That's fascinating. The style transfer stuff in GANs is just absolutely fascinating.
This is true.
Especially when with respect to like what makes art change over time. The novelty aspect of art is just fascinating. So, okay, enough divergence.
Like were you there in this like deep learning NYU course when Jan Lekun that there's one more channel.
Mm-hmm. Okay.
So this Alfredo one that course is really awesome, I would say. Anyway, so we started. I mean, the page rank is basically, I mean, same thing. The idea is to identify the value of a node based on how many times one person, a random person, if he starts going through the direction in which he's pointing, he's been pointed out. So how many times one visits that node? So that would be some sort of importance of that node,
Okay.
that
So
web page.
independent of its reputation.
Yeah, so
Yeah. Okay.
the reputation will be corresponding to how many times, like obviously normalized, how many times one is going to visit that specific page.
Oh, so
So,
but what?
yeah.
Help me with the understanding of reputation with respect to citations and being in a, an encyclopedia, kind of giving a page just some de facto high reputation versus the visiting gives it another aspect of popularity. I guess they work together. That's why we're doing this.
Yeah, so I guess what reputation is some sort of a like the weight of that node will be a proxy for that reputation. So reputation is based on how many times one, like how important that page is. Maybe that's what they are calling.
Authoritatively. Yeah.
Right.
Okay, got it.
So
Okay.
okay, so the page is more important if it has more links, incoming, outgoing links, and okay. So this like Stanford that edu has 25. There's many
Right.
links, but this does not have one link. But I guess this is getting visited
Yeah.
much more often. Okay. Yeah. The point was the link.
Everybody wants to link to Stanford, so it's called important, or it's got a high end links. Yeah.
True.
Okay.
Yeah, and it has got links from other high reputation pages, so that counts.
Right.
So in the end, if I am going, and those high rank pages, like those high value pages will have again incoming links from other high other high value pages.
Right.
So if I'm just traversing the web randomly, I mean, if I'm going to a node, I'm randomly choose the out node from there, and I end up on some other point. So in the end, the number of times if I keep on going that infinitely, so the number of times I will end up at Stanford's website will be much more than any other, like this person does not exist .com or on here.
Yeah, but by virtue of the number of high end
Incoming
links. Yeah.
high end links. Yeah, that is the correct point. Now the thing is, like, how do we figure it out? Because you cannot have this you cannot be traversing web infinitely. So okay, this was the idea, like the vote being the number of end links, the normalized by how much valuable those end links are there. How do you define that? So for example, if in this I node has how many 3 outlinks, and if the reputation of I node is Ri, then for this node the contribution from this link coming from I will be Ri by 3 because there are 3 outgoing links. Similarly, for this K node, I mean K web page or K node, that's what we say. There are 4 outgoing links. So the contribution here will be Rk by 4. So the importance of this will be total summation of all the possible incoming links which are coming. And the same way, subsequently, it will divide its reputation based on like how many outgoing links are there. For example, for J, we are getting Rj by 3 here, then again 1 by 3 and 1 by 3.
It passes it
yeah.
on.
So we pass like that's the whole idea, that we are getting the value from different nodes based on how many outgoing links are there, and we are
R
passing
sub
those
J.
out.
It doesn't. Yeah, I thought that was R sub I. It doesn't pass the value that it got from node I onto node blue.
True.
Okay. Thank you.
Yeah. So
it's
it is like basically total sum of that, and we divide it by 3. Yeah. So so we are defining, then we define R basically, let's call that rank, and we define them as summation of Ri by Di, where the I represent I to J represents or like how many outlinks from I are in links to you.
So would it be in Stanford's benefit to have 0 outgoing links?
I guess so.
Stand alone at the top of the mountain?
But no, I don't think it was going to affect it, because in the end, whenever you are it doesn't mean that the values of this Ri gets reduced when it is contributing the importance to other nodes.
Okay.
So it's not basically we are not losing out on that reputation. I'm just like more of a we are keeping that, but still saying okay, you get this much importance from us.
Okay.
So, but this is fine. Like you can have some sort of a like now there are basically caveats on that. You can have a link to yours. You can basically link 1,000 links to yourself,
right.
And you have so many incoming links. But I guess this will take care of that. Okay.
Then the flow equations. Okay, we got the equations of those flows, which are going to come up later.
Yeah. Okay. Yeah. So that's what it talks here. Like let's page J have TJ outlinks. Then if the problem with this is this, and like whenever sometimes the mathematics he does is sometimes I mean I really don't like that he keeps on moving J from inlink to outlink. So you say DJ have outlink, then I move to GI. But here it is. So initially it confused me a lot, because he's defining those importance metrics in terms of DJ. But in the end, whenever he goes here, it is defined here. It is defined in terms of I.
Yeah, so, somebody mentioned that some time ago. They said that the subscripts are very loose.
Yeah. So, yeah. Initially, it like basically, I was not able to understand. Like I was not able to figure out what is happening. Where am I getting this wrong? Then this whole subscript thing was there. Okay, so what he's defining here in terms of like if I call MJ as the column stochastic matrix, maybe I would say like an importance transfer matrix. That's what I have been saying this. So you see,
right.
Again, he's jumped from DJ to again DI here.
Sure enough.
In the same page. That is bad. So it's R is equal to MR, and that becomes what it is called, Markov something, right?
The distribution? No.
Markov equations. Markov.
It's a Markov chain.
Markov chain.
Is that how it converges?
Yeah. So you basically if you sum up column wise, it basically sums up to 1.
Yeah.
So what happens that you can solve this to get based on the eigenvectors. You can solve this to understand what will be its without even going through infinite iterations. It will what will be its resting state, like
final state,
stable state. Yeah, final state. The explanation again. So at time t he's here, and at time t+1 he's here based on this transverse matrix.
A random observation. Like, do you notice like in the previous slide the title of the course is wrong at the bottom?
Okay. Oh, mining. Oh, boy. No, I did not. Yeah. Oh, okay, it is 224W.
That was probably from 5 years ago. They probably don't. He used to teach that class, I presume.
I think there's a CS224W. I think the last iteration is actually 2019 because that's the one that they do like Spark and stuff. But they must I think there must be some overlap and they just reuse the slides. But I just find that quite funny.
Yeah, I didn't notice that.
Some year back, I had started this this MOOC, but maybe like 1 or 2 classes I stopped because it got so boring.
Yeah.
And I haven't done this. So, okay. So yeah, basically that again repeating the same equation I to j. Thankfully, we are back to I to j, and so that is the same. It basically represents this matrix. We can represent it as matrix, or we can represent it as this rj is equal to this. So rj will, if I say rj, it will be I can call that what should I say? Maybe so if at a point t he is here, he can trace his paths. I mean that random surfer can trace its path based on this equation, which is equivalent to this equation. This matrix equation.
Yep.
Okay, so this process repeats
yeah.
infinitively, etc. So now he starts with pt, a vector whose coordinates is problem, that is surfer is at problem page p, and pt is the probability distribution over pages. Basically, if I have just 3 pages, so it will be probability distribution on this, and based on that probability and where that surfer will randomly end up, that forms some sort of a reputation. Higher your probability, higher will be your reputation. Now, what will be the stable state of that reputation? It basically is solved by solving this equation. So where r is equal to mr, you go through this. Okay. Then he traces back to eigenvector centrality, relates it to this basic. So what this eigenvector centrality gives is what the solution to this.
Right, that makes sense.
That makes sense, right?
Yeah.
So if I solve this equation r is equal to mr, we are able to figure out what will be this stable state of that. So that r is the principal eigenvector of m with eigenvalue 1 whenever that is found.
Apparently, that was the big thing about PageRank, was that realization right there about the random. What happens when a random walker, and if you can solve that, then you can accurately sort by importance.
True.
Or something. It's magic. So yeah, I don't quite understand exactly all that math, but I understand the way it's laid out and the way it's solved. I was able to solve the homework. I think we had a homework with this, didn't we? At one point.
I did not solve this. Okay.
Was that homework 1 collab? Where did
Yeah,
we
it's a collab or homework somewhere.
Oh, was it there? Is it eigenvector centrality? I don't remember. So there could be. Right? I think there's a direct this for that. The direct function for that eigenvector centrality. If I remember correctly, in network I used that.
I forget where we did collab. Collab 0.
It must be in collab 0. I don't think it was in collab.
I actually did you make the or did I do the matrices on paper? I think I did them on paper. Yeah, I guess I did them on paper and was able to figure it out.
Well, that's like the page rank in collab 1.
Oh, was it?
Sorry?
Was it in collab 1?
Yeah, question 3. You have to implement 1 iteration of the page rank algorithm.
Oh. Okay, that's why I had to figure out the formula. Everything. Let me open that up real quick. Make sure I understand.
In collab 1 or collab 0? Collab 1 was it?
Collab 1.
Collab 1. Okay.
One iteration. And
page rank value of the node 0. Right. Correct. What did I do here?
I don't know why I got this. How did I get this? Yeah, you divide by the number of nodes, R0.
Yeah. R0 by G degree. I mean, that's what I did.
Yep. I actually have a thing where I calculate a contribution, which is 1 over the length of the other ones or something like that. And then
I did the 2-directed one here. Okay, so I guess again I did
yeah.
what you were doing earlier. I should have maybe pulled it as a directed graph
Matter
itself.
of fact, I think I got the right answer because after one iteration, I got 0.13. And then after using the PageRank from Network X, I guess it converges at 0.09. After
Oh, then I got it
So
wrong.
what
is
you
that-
can, so you can actually check it against the NX of PageRank if you set max iter equals 1 and set a really high tolerance.
Good one.
Then you actually can for like questions, there's quite a few and basically you can like assert that they're equal. And I think in question 1 and 2 as well, you can check your results against like the network X.
Yeah, by forcing it to just do one iteration. Okay. That makes
So
sense.
like after one iteration, I got like 0.0669, something like that. I don't know whether it's
maybe.
I got 0.128 for
did you take it as a directed graph or indirect? Do we have any? Does PageRank work on undirected graph? I don't think so. Is it? Because there is no concept
No.
of in and out nodes.
No, you need to convert it into a directed graph.
But if I am converting the undirected graph to a directed graph, then I lose that information, right? So as we in the Dave's case, that was happening. So,
Sure enough.
No, you are not, because you're converting an undirected graph to a directed, not the other way around.
Oh no, undirected graph to directed creates problem, because when I have undirected graph, it already has thrown away the pairs which are which had the same elements but were in different order.
No,
So
one that you like in the PageRank you pass in a graph. So if it's so the graph it should be the correct form. So if it's originally a directed graph, it should be a directed graph. If it's undirected, it should be undirected. And then in the function itself, you check if it's directed, and if it's not, then you convert it into a directed graph. So you don't lose information by converting it to an undirected graph and then back to a directed graph. Does that make sense? Because I think they're running the examples running it on the Karate Club, which is itself it's undirected. So
true.
You're not losing any information there, but because you need to run PageRank, you need to convert it to a directed graph.
For the wiki thing, right? So where they had the PageRank question, I think it was a Stack Overflow, sorry. I basically wrapped, so when I loaded, I said NX read from, the text file or whatever, and then I wrapped whatever came out in NX digraph. So that created a directed graph out, kind of forced it into a directed graph. Just,
Interesting. So the directed graph, undirected has all the raw nodes in one direction only, right? All the connections, but only in one direction.
that is directed.
And then
directed means both,
Right. So if you just read it in, doesn't it?
It probably does, but not sure.
Okay, that would still work, maybe. So how can we do like PageRank on undirected graph? Doesn't seem to make sense.
That's why you need to convert it to a directed graph before doing anything, because you need the
So if it converts into a directed graph from undirected ones, then based on whatever the ordering is there, it will assume that as the direction of the
both ways.
edge.
It'll assume both ways, I'll bet, if you load it in.
No, I don't
No?
think so. It will
Oh.
basically take the, I mean, the direction of the edge, whatever is there in the undirected, when it is storing, the way it is storing the edges, it will take that direction only. So if you remember,
No.
Dave,
I think
uh,
doesn't it? I need to
let,
look up,
let
but I
me
thought it
actually
was
run the
like it
question.
creates edges that go both ways, doesn't it?
I think that was happening in the Dave's case, right? When he was taking that Wikipedia one into account, and he read it as a undirected graph, so it already had lost that information. When he converted that back to a directed one, there was no information of that the reverse node coming. That's why he was getting
Zero.
some of the values zeros.
Yes.
So I believe that whenever we are converting, whenever we are taking the directed graph and converting to undirected one, we are losing all that information, and it won't create two directed edges in place of one undirected edge. It will just interpret the direction, the ordering as the direction of the edges. It could be other way around ordering, because maybe that, I don't know what is the way it is throwing away, like the direct out of the
Right.
two pairs. So I guess it is like whichever comes first, it will take that into account. It will create directed edge based on the ordering itself.
Right.
So we are losing information there, and we have lost,
Um,
as we had lost information, we cannot get it back when we're converting from a undirected one to a directed one.
Yeah, I can confirm this. I just ran this thing without the casting NX digraph. So, and I see that when I say nx.info on the G on the graph, it gives me type graph. Whereas if I cast it to NX digraph by wrapping it in nx.digraph, it gives me type digraph. So I can post this maybe.
And how many nodes? Does it
I
actually
just
double the nodes? Or does it not double the
No,
double the edges?
The edges are half the edges. That's interesting.
no. If you look, so I'm looking at documentation now, and if you use the to directed,
No, yeah. So what Wendy like
it,
when you are reading it as a directed graph itself, then it is fine. But if you're reading as an undirected graph, or maybe if you are reading as a directed, then converting to undirected one, then you're losing information there. That was my point. So that's what happening. What I feel is happening was in case of Dave also, when he was doing that, when what he shared for the homework one.
Guaranteed. Yeah. Sujit, earlier I had an example of reading in the wiki, but I read it in as a undirected graph, and it lost all the reverse pairs.
Okay.
Yeah. So we're trying to kind of riff off of that and trying to have context here with Karate Club.
but it's different because Karate Club itself is not a directed
Not
graph.
directed, correct.
Right.
So basically, like when you convert it to a directed graph in the PageRank, it actually creates two edges per edge of the undirected graph.
Really?
So if you look at documentation itself, there is like to_directed function in networkx, and it basically creates two edges
Okay.
per
Explicitly.
like what? Yeah. So per edge in the undirected. So you're not. It's not kind of some random direction that's assigning to each edge. It is like both ways.
Okay. Okay, well, that's nice. So then you can actually run PageRank on Karate Club if you do that step. And I don't think I did that step. And that's why I got such a wrong answer for PageRank. When I choose PageRank iteration 1 using the NX PageRank, it said it does not converge and it errors
Yeah,
out.
you need to set a really high tolerance because it assumes that it will converge to under the tolerance.
Got it.
And the default tolerance is like really tiny. So I just use a really high number.
Thank you. Is that beta?
It's a parameter. It's a keyword argument called TOL.
Which has a default value of something quite small.
Yeah.
What would be a good number? Let's see.
For me, I use 1,000.
Tolerance of 1,000.
Yeah, so
Oh.
you're actually, you don't care about convergence basically.
Oh,
Tolerance
okay.
is the difference.
It'll
in
always
the,
it'll always meet it. No matter what you do, it'll
Exactly.
always
Right, right.
satisfy that one. Okay, good. So I actually did it. After one iteration, I got 0.128 from the NX PageRank, and my algorithm was 0.13. So I think I did the algorithm properly, but maybe on a improper representation of the graph. Yeah. Okay, I'll go back and figure out how to make it into a directed graph. Oh, great. This is very helpful. Very, very helpful. Okay, so I think we're at a point where we fully covered at least the PageRank, the matrices and the derivation, and progressing through one iteration was very helpful. We already walked through a bunch of stuff with NetworkX before on directed, and started in on the Wikipedia, but we didn't go much further than the first couple of questions. Sujit, you said you did a pretty good effort going through that?
Yeah, it's not that hard.
Okay.
So I went through all of them actually.
Yep. So I wonder if it's worth, because next week, man, we're going to be into some more material that's way past this stuff.
Right, right.
So
do you want me to share? I mean, I could.
Well, I'm getting to a point where it's almost a point in the day that I need to stop.
Okay.
So I'm debating if we need to maybe back off just one lesson, or I don't know, other people, who knows where they are. I almost want to spend 1 week just getting all this together, but I could probably say that every week. Any opinions?
So I guess based I have to have that understanding of the embeddings thing, which I have to test those stuff which we are discussing, whether the understanding is correct or not right now.
I think it would be, the collab is definitely makes you think through how that works. Random initialization, everything.
True.
Well, all you're doing is you're embedding the weights of the embedding layer with uniform distribution. So that's what is reflected in the first visualization, right? Where it's all jumbled up. And then when you train the model for 400 epochs, basically you get a much nicer separation on the weights, right? So
yeah, we actually had a discussion earlier just trying to understand the negative weights, negative edges, and trying to understand how that impacts the whole derivation, just how it works. So that was a good.
Negative weights you have to have because it's a kind of a classification problem. You're trying to the pretext task is a classification problem, and so you need negatives as well as positives for the machine.
As Vigas pointed out, you're trying to drive the energy to zero of those edges.
Okay. Yeah.
That's a good way to represent that. And to me, the embeddings are just very fuzzy because they really aren't anything but a latent space representation.
Exactly.
Which is just weird. Is it arbitrary how many you choose? 77?
I think that's the number of positive edges. So here they followed the rule of thumb and said, let's choose exactly the same number of negatives for a typical classification problem.
Well, for the number of embedding dimensions, you mean?
No, the embedding dimensions were 16, I think, right?
Right. Why? What number? How do you choose that number?
It's arbitrary. It depends on how much expressive power you want. So they chose a 16-dimensional thing.
Okay. So if you chose 2, it just wouldn't work.
It would. So when you do the PCA, the visualization, I think it uses PCA. I'm not sure. It does some kind of dimension reduction.
Okay.
But to have that, you need enough dimensions for it to be able to separate out the dimensions, right?
Right.
So
just like normal like linear algebra thinking about power of something. Yeah. Okay.
Right. Intuitively, if you think of it like, high dimensional space, you know how there is the curse of dimensionality where, in high
Right.
dimensions, everything is close to each other, but everything also has room to, go away
Express.
from each other. Yeah,
Yeah.
exactly. Right. So the more dimensions, the more expressive power in that sense.
Okay, that's very useful. That's all. That's the only mystery I had really, but I'm just trying to think of whether I'm ready for 6 and 7 in 1 week. Personally, I would rather get better at what I currently have in front of me than venture into, unless it's complementary. Is 6 and 7 somewhat complementary?
I think it's graph neural networks. It's like the next
using
type.
using embedding layers, just more on.
Yeah, I'm not sure. I haven't actually gone through it. I just know from the high level.
6 and 7. I'm looking.
I mean, they are. So I'm going to 6 at the moment. They are fairly related. I mean, because let me remind myself what the topics on 6.
Even 5. I haven't even looked at 5 yet.
Yeah, the pace is kind of brutal here, but it seems to be working. I mean, the original intent was to get it over and done with in like 2.5 months or something. And I think, it is working.
Okay. Okay. I just need
At
to,
least for me.
Yeah, I agree. That's a good point. I just recently stepped it up a little bit. So that's just telling me to step it up again. Unfortunately, I have visitors all week coming up. It's going to be kind of a rough one, but the material is just interesting enough to motivate me.
Yes, that is true.
And so and I've already done a lot of CNNs and things. So this does look fairly just more applying those things to this new construct. Okay, let's just go with it.
Kind of. So I mean, like half of lecture 6 is just reminding you what like neural nets are and backprop and that thing. So it's actually not that hard.
Sure enough, gradient descent, the whole thing. Backprop. Oh yeah. Okay, this is kind of a review of deep learning. Okay.
Pretty much. I think there's like starting to be a bit of like actual graph neural nets towards the end of lecture 6, and then I just probably more in lecture 7. But lecture 6, if you have already done like CNNs and stuff before, is probably going to be quite easy. Yeah,
I'm scrolling through it and it looks okay. So I think this is basically saying strap in. Like you're right. It is getting, the pace is going to go quick, but the material is just excellent.
Yeah, it is.
And I think he's a very, very, very good lecturer. When you watch his lectures, you do understand what's going on. It's just doing the assignment, so that's sometimes a bit harder. Yeah, that's true. That's always the way it is. Conceptually, stuff does make sense if you have any understanding or background in the material, and can take it just a step further. But then when you actually have to implement it and get the array sizes to match perfectly, whatever, using a tool, any application oriented task takes minutes and hours. That's the nature of life. Yeah. Okay. All right. Well, I'm going to take off for the day. And thanks a bunch. This was a good session, like usual. I think as soon as we start diving into the examples, it gets good because everybody has a perspective and if things are right or wrong. So I think do we have homeworks next time? Probably not. It's actually collab 1 that's supposed to for next week. Okay, good. And you seem to be halfway through it anyway, so. Yep. Okay. I think we'll
So one question, like I was looking at this page rank thing on the collab 1. So the alpha there is the beta of what so in NX page rank there is a parameter called alpha that is same as the beta parameter what we are defining in our iteration, like where we have to write that the function, right? The damping criteria.
Yeah. Yeah.
Yeah, right. Okay, cool.
Yeah.
Because now my results are matching. Oh, nice.
Just to make it confusing.
What is beta? Do we have that above somewhere?
So
Yeah. Like
yeah.
the one in the equation, like it says implement the patron equation Rj equals like that thing, the beta. And then in network X, they're calling it alpha.
So yeah, that is basically to define that we do not get stuck at some node which ends in something or
Oh, right.
basically redirects to itself. So randomly with a probability of 1 minus beta, it will jump to some random node in the whole network.
Right. Where is, so NX PageRank, oh, alpha equals beta. That makes total sense. Well, that's even bizarre. Just that. Just, oh, they chose the wrong Greek symbol.
A lot of
Right.
times.
Yeah. Okay. Okay. Well, thanks. I'll see you guys next week, and I'll try to participate more in the chat, but it's hard. It's tricky during the week. But I hope we don't lose people. I think we might be losing a few, feeling like they're maybe not getting a lot of participation.
And the pace is comparatively faster, and that could be one reason.
Yeah, you cannot do this casually. I've learned to only do one at a time. This kind of involvement, if you're involved in regular life plus a job, if you have time for more than one of these, wow, you're a great, you just have a brain you have too much time on your hands. Okay, very good. Nice to talk to you guys. See ya.
Cool. All right.
Yeah.
Bye.
Yep. Bye-bye.